Hello, today we'll be starting on our first lesson of the differential calculus. And even in the differential calculus, we will be discussing about the very first unit, the rate of change, and the definition defining the first principle, also known as the differential coefficient. Without any words, let's start with the rate of change. However, before starting, I really want to emphasize, since this is the very first unit, since this is the very first lesson, we'll be going over the most fundamental tools and concepts that will be used directly through to define other identities and concepts later on. So I think a reason why a lot of people are actually having a hard time with calculus is they don't really have the really strong fundamentals. And because of this, I really want you guys to actually not just memorize what I will be discussing today, but to genuinely grasp the concepts that I am talking to you guys. So really try to holistically absorb the knowledge so you guys will be free to apply these concepts to other students or your assessments and homeworks later on freely, because this, I guarantee you, will be the biggest key to lead you to success in this so-called notorious unit of calculus. Okay, without further words, let's begin our lesson of the rate of change. So in general, what is defined as the rate of change? Well, and I do not really know what kind of connection it actually has with calculus. Well, more professionally, you might as well already know what the rate of change already means. However, saying it more specifically, the rate of change is defined as the measure of change of a variable per a unit of variable. Well, this sounds very generic and very confusing, right? So let me give you some examples that might actually help you to understand. Let's look at velocity, speed. What are these represented as? Meters per second, right? The number of meters that you travel per second. So the measure of change of meter per unit of second. Isn't that surprising? Isn't this congruent literally 100% with the definition of the rate of change? Yeah, so these velocity, speed, let's say the amount of change of energy per mole, kilojoule per mole, such as in physics and chemistry, all these units are the examples of rate of change. This is pretty much, this example boasts your understanding, right? Well, however, we're not really, what we will be talking about is literally the same as the velocity and the change of energy per mole. However, let's kind of bring this energy, let's interpret this definition of the rate of change into more of a mathematical term. Let's tailor it more to a mathematical so-called rate of change. So I said that the rate of change is defined as the measure of change of variable per unit of variable, right? However, in mathematics, rate of change is usually applied onto a function. So what does a generic function have? A generic function is two-dimensional, right? That we discussed in high school. It has x-axis and the y-axis. And then usually in the mathematical realm, the rate of change is defined as measure of change of x per, oh my bad, of y per x. So, just like the other rate of change, the variables, however, in the previous example for velocity was meter and second, joule and mole. However, in this case, in mathematics, in functions, the rate of change is described as the measure of change of y per change unit of x, per unit of x. Unit of, my bad. However, and then how will this be represented in an equation like this? Well, simple enough. Well, this by definition was the amount of change of meters traveled per second. The amount of change of energy that is released or absorbed per consumption of 1 mole of compound. Then this, in the same way, the measure of change of y per unit of x. Then it will be literally represented in change of y per unit of x. Okay, And doesn't this kind of surprise you? In a function, the change of y over a change of x is also described as the gradient of the function. So basically, in this case, the rate of change of a function means the gradient of a function. Wow, that's pretty surprising, right? Okay, well, if it's not surprising, I'm pretty sure you'll be surprised by the end of the class. Okay, so we defined the rate of change in a mathematical way. However, this rate of change does not end here. The rate of change is actually classified into two distinguishable factors. One is the average rate of change, and the second is the instantaneous rate of change. First, we will be defining and learning about the average rate of change. So what is the average rate of change? Average rate of change. What is it? Well, average rate of change surprisingly contains the same meaning as the rate of change, however. I'll just be combining this, promising this as definition. So the definition plus on average in interval. So although it might be a little confusing to actually understand, so this is saying the average rate of change is defined as, the definition recalls to the most common definition of the rate of change. So the average rate of change is defined as the measure of rate of y per unit of x on average in an interval. So what does this mean? Well, the word also itself is very hard, right? So just generalizing it, it just means you're calculating the gradient of a function, however, in a specific interval that you choose. And how is this gradient calculated by? Well, let me show you. It's better to just show you in a function. Let's just draw a function y equals fx. Let's say this is a function y equals fx. And let's grab 2 points, a and b. A and b. And so we chose the interval, right? However, if we want to calculate the average rate of change in an interval of y equals fx, x from x equals a to x equals b, then how do we do this? What gradient are we finding? Well, the average rate of change asks us to find the gradient by connecting the endpoints of the intervals that corresponds to a function value. And if you simply connect these two values, these two coordinates, and calculate the gradient from the line that has been created, then that will be the value of the average rate of change of function y equals fx from the interval x equals a to x equals b. Very simple, right? This simple calculating the gradient thing was what we have done since middle school. However, describing this in words is pretty lengthy, so I'll try to generalize and represent this in a mathematical equation. So, okay, we want to calculate the average rate of change between a and b, so we have to calculate the change of y over change of x to calculate the gradient. So, what is the y value of this coordinate? Well, it's very easy. If you just plug in a to fx, then you'll get the value fa. And for that, when the x equals b, the y coordinate will be the fb. If you just plug in b to fx. And if you want to calculate the gradient between these two endpoints, it is very simple. You have done this so many times before. So the average rate of change can be calculated as the change of y over the change of x. And what is the change of y? fb minus fa. This value is the change of y. And this value is the change of x. So therefore, for the change of y, it will be the distance between these two fb and fa. So if you subtract fb and fa, this will give you the value of change of y. And for the change of x, if you subtract b from a, that will give you the value of change of x, because the change of x is same as the distance between a and b. So this is the generalized form of the average rate of change between the intervals a and b applied on the function y equals fx. However, surprisingly, there's a different way, or more popular way to represent this equation, the average rate of change. Well, it represents the same equation, however, there is a different way to express it. And I'm going to tell you right now. In this equation, you can also see that b is delta x bigger than a. So you can put this in another equation of b equals delta x plus a, right? And in this same equation, I'm going to substitute b into terms of delta x and a. If I do that, then I'll put this as the first equation, and for the second equation, b can be represented as delta x plus a minus a. And b, with the same substitution as done in the denominator, can be represented as f delta x plus a minus fa. Pretty complicated, but looking cool, right? However, surprisingly, there are two a's with the different signs. So a minus a, we can cancel them out, which just gives us just delta x. So these are the same equation, the two equations that represent the average rate of change between a and b. This is more of a direct format that we have done since middle school. However, this is a different way that has been done from the substitution of b into terms of delta x and a. So whatever new things we have learned today about the average rate of change, until this point you guys have already learned before. However, in this class, you have learned a different way to express the average rate of change, which is the second expression as shown. And the reason why I introduced this other method, you will be able to know when we actually learn the instantaneous rate of change, which is the other type of the rate of change. Okay, so I think you guys have mastered this concept. Oh, however, let's just go over this if you're pretty much confused. It says on average, right? What does this imply? This implies that we're looking at the average change. So we're not considering like every single minimal trivial changes that happen between the intervals. For example, let's say like the function like went over like this, like up and down, like over the ranges of fa and fb. However, because it is the average rate of change, it only has interest in the beginning and the end point of the interval. So it is only interested about the resultant change from the beginning and the end point. So it does not take consideration, it is not interested in any point alterations in between these two intervals. So that's why it is called an average rate of change. So maybe in assessments or other questions that you're solving, you're encountering the function where its graph like goes way up and down between the intervals that you're trying to find the average rate of change from. Don't be confused because you're not considering that, because by definition, you're only interested in the beginning and the end points. So that is again why I am saying that these general concepts, these general definitions are crucial for your success in a difficult questions or tricky questions. Okay, so if we understood that, let's go over to now the concepts of the instantaneous rate of change. You guys did a fantastic job on the average rate of change, and I'm pretty sure you'll do the same on the instantaneous rate of change as well. Instantaneous rate of change. So, just like the average rate of change, well, the instantaneous rate of change also entails the same meaning from the rate of change. So I'll write the definition again here, which is a connotation for the definition of the overall rate of change, which implies the gradient of the function. So, however, unlike the average rate of change in which its gradient was calculated from the endpoints of the intervals, or we needed the interval to find the gradient from, right, to calculate the average rate of change in a function. However, for the instantaneous rate of change, this is defined on specific point. In other words, we're trying to find the gradient on not 2 points of a function. However, we're trying to find the gradient specific on 1 point of a function. And probably if this is kind of hard for you to imagine or understand, let's draw a same function on this line here. Y equals fx. On the first graph, we chose the interval a and b, and we chose these two coordinates on the endpoint of the intervals. Thus, from our convention, because we have two coordinates, we were able to successfully find the gradient between these two coordinates. However, in this case, this is asking us to find the gradient from a single point of A. The tangent line from a single point, this point. So to find the instantaneous rate of change at a certain point, let's say x equals a, then we are trying to find the exact gradient of this piece of a function. So this piece of a function y equals fx, we're trying to find its instant gradient where it passes the x value x equals a. We're trying to find the instantaneous gradient of this function f equals x when it crosses the x value x equals a. So how are we going to do that? Well, I told you from before, from the instantaneous average rate of change, we used two coordinates. However, in this case, we only have one coordinate, right? And, you might ask me, are we going to learn right now a new skill that we can calculate this instantaneous rate of change by using one coordinate? Well, we eventually will. However, we still haven't learned it yet, right? And to actually define that formula, to actually derive that formula, we still need to apply the concepts of using minimum of two coordinates to find the gradient of something, right? So what it means is that up until now, we can't calculate this gradient. We can't calculate this red line, the gradient of this red line with only one coordinate that has been given to us. So what are we going to do? Well, actually it's pretty much hopeless, right? However, I really think the mathematicians are genius. Well, we said that we at least need minimum of two coordinates to find the gradient of something, right? And if we dearly want to calculate this gradient, then we're never going to find it with just one point. So let's artificially make 2 points to define this gradient. Although it's not exactly this gradient, let's try to approximate this gradient. That's what the mathematicians thought. And I really much think that they're a genius. So just like they said, let's grab another point on the right side of A and let's define it at x. And on the first graph, I defined this value as b because to show that it is a fixed point that it cannot move. It has a specific number to it. However, by defining this point x, by defining the second coordinate as x, I am saying that this point is free to move around on any point of y equals fx as long as this function is defined, as long as that it is in the domain of the function. Okay, so what the mathematicians did, they calculated the average rate of change between these 2 points. So what does this imply? Well, I'll be using a yellow line here so you don't get confused with the actual instantaneous rate of change at x equals a. By connecting these two lines, we get the gradient, the yellow line here. And you can see it is bigger than the red line, which is the answer that we're trying to get, right? However, I have told you from the beginning, before calculating this gradient, that x is a free point and it can move on any point of y equals fx as long as it is defined. So let's move this a little more closer. Let's move this x a little more closer to a and calculate the average rate of change again. So let's imagine x moves about halfway of the distance to here. Then if I calculate the gradient one more time, it could be messy, I'm sorry, but this gradient, the second gradient can be calculated like that. So the tallest graph right here. So it is a little more flatter than the first gradient that we drew. However, it is still a little bigger. It's still a little steeper than the actual instantaneous rate of change at x equals a. However, on the same convention, let's continuously, well, I'll bring out my weapon. Let's continuously approach this gradient closer to a. Let's continuously approach this gradient closer to a. As x infinitely approaches to a, then the average rate of change of these gradients will slowly flatten out. As x infinitely approaches a, you will be able to see that the gradient slowly approaches. The average rate of change between these 2 points will slowly approach to the instantaneous rate of change at x equals a. So at the end, as x infinitely approaches a infinitely close, then the average rate of change between these 2 gradients, between these 2 coordinates, will eventually infinitely get closer to the instantaneous rate of change at x equals a. So what are we trying to define by this convention? Well, first, just by putting it into words, I was saying that the average rate of change between x and a, we're finding this initially, right? However, as x infinitely approaches a, the average rate of change between these points apparently slowly approaches the instantaneous rate of change, the pink line, the instantaneous rate of change at x equals a that we were trying to find. So by using the concept of limit here as x approaches a, as x approaches a, the average rate of change between x and a will be closer to the instantaneous rate of change at x equals a. However, so it will get closer to the instantaneous gradient at x equals a. However, there is a symbol to represent the instantaneous gradient at x equals a. It can be described as f prime a. And this is the new method that you will use to symbolize the gradient of a function at a certain point. So let's say like f prime 1, then it shows the gradient at x equals instantaneous gradient of function y equals fx at x equals 1. If it is f prime 1000, then it will be the instantaneous gradient of function y equals fx at point x equals 1000. So, rephrasing one more time, as x, a free point, infinitely get closer to a, then the average rate of change between these 2 coordinates, these 2 points, will eventually approach the instantaneous rate of change at x equals a, which can be symbolized as f prime a. Okay, however, you need to be able to ensure that the average rate of change between these 2 points will never actually be exactly equal to the instantaneous rate of change at x equals a, because imagine where x is actually equal to a. For this gradient to be exactly the same, then x needs to be exactly equal to a, right? Because imagine if x is, even if like 0.000001 unit to the right side of a, then the gradient will be a little bit bigger than the instantaneous rate of change. However, let's say if the x is exactly a, let's plug in a here and here, then it will be 0 over 0 condition in which the limit will not exist. The limit can have millions of values. Thus, the gradient x needs to be infinitely approaching a. However, due to this limit, because the utilization of limit always signifies the destination in which this average rate of change is approaching to, this converges into one value. So rephrasing one more time, x cannot be exactly at a, because imagine if x is exactly a, then this whole value, this gradient, will not be defined. However, if you use limit here, the limit symbolizes the destination in which this equation is approaching to. The destination in this equation is infinitely getting closer to. Thus, although this value will never be the same, although this average rate of change will never be equal to the exact value of the instantaneous rate of change at x equals a, still, by using the limit, it is saying the value in which this equation is approaching to. Thus, we are able to say that the limit of this equation is exactly f prime a, which is also known as the instantaneous gradient at x equals a. I know this can be very confusing. However, I will make sure to rephrase it again during our next class. So, this is the first method of representing the instantaneous rate of change at x equals a. Okay? However, I've told you, so surprisingly, you'll directly be able to see that the concepts of average rate of change from here was directly used in the smooth transition to define the definition and the identity of the instantaneous rate of change. And since there are two ways to define the average rate of change, then let's try the same way. Let's try another way to define the average rate of change. So, in the same concept, we will use the process of substitution. So in this case, x is delta x bigger than a, right? So x is a plus delta x, showing that it is delta x bigger than a. By applying the same format, then, so substituting for x in terms of delta x and a, it will be delta x minus a and f a plus delta x minus fa. And for the limit, it will also be representing x in terms of a and delta x. It will also be a plus delta x approaching a. I'm sorry if it is a little messy, but you will also be able to see that a cancels out, just leaving delta x. And since the limits have both a's at both left and right side, they will also be able to be eliminated, leaving just delta x and 0. So this also makes sense, as the distance between a and x, which is the delta x, as x infinitely gets closer to a, then the delta x, which is the distance between a and x, is also infinitely approaching to 0. So this geometric representation and the limit representation coincide, are the same, are symmetrical, making sense, right? So this, again, as this equation is also equation for the instantaneous rate of change when at the point x equals a. And however, this equation still also works, still also satisfies the equation for the instantaneous rate of change at x equals a. And this equation was derived with the same principle, with the same process as defining the second equation for the average rate of change. So you will be able to see the similar patterns between the two equations. So the second equation. However, in the mathematical world, mathematicians have promised to themselves to define the delta x in terms of h. So if we change all the delta x in terms of h, then you will successfully be able to get this equation, the brand new equation that is derived from. Well, although it looks very different, I just have changed delta x into a terms of h because that was the promise that has been made by the mathematicians in the mathematical world. Yeah, so these are the two ways that can be represented as the instantaneous rate of change at x equals a. However, the most surprising thing, the reason why I have introduced this topic, not just this topic, is because this format is used more widely. This format is used as the basis, as the basic unit. So this formula, although it still works, there's no problem with encountering this problem with this formula. there's no problem defining this equation as the instantaneous rate of change at x equals a. However, this equation is used more prevalently throughout all the mathematical curriculums. So this is why this is actually defined as the first principles. First principles, also known as differential coefficient. So you will be able to know. So basically, the instantaneous rate of change is basically can also be defined as the first principle. So those are the connections that we have for today's lesson. So for today's lesson, we have learned the definition of rate of change, and we have tailored the general definition of the rate of change into the definition of rate of change in math, which is applied to functions, so which also implies the gradient of a function. So by stating this general definition of the rate of change, we applied this definition to define the other two types of rate of change, which was the average and the instantaneous rate of change. And by using the concepts of the rate of change here, we also defined these exact concepts of the average rate of change, and able to define and derive the formula and the equation, and also the concepts for the average rate of change by using not only the average rate of change, but also the concepts of limits that we have learned throughout the previous lesson. And since we had two equations here, we were also able to get the two equations that we wanted for the instant. Okay, so one more time recapping. Because this formula of the average rate of change is the formula that you have encountered since middle school. So you are already very familiar with actually understanding and using this formula. However, to able to get the equation that the high school actually expect us to know, we only had to make a minor process, minor equation manipulation of substitution to get the formula that we desire to have. So that is why I first introduced the both average rate of change and the instantaneous rate of change with the familiar equations that you were already knowing, so that you would only need to make a small data manipulations to easily get the formula that you wanted with thorough comprehension and understanding. So this formula actually, I can guarantee, will be the most significant formula that you will have for this unit of calculus. Although it may be easy, thorough understanding is necessary. So yeah, I think that was a very smooth transition. And before finishing the lesson, let's try some real life example that we have never tried of. For example, in this box, if I want to calculate the gradient of x squared, which is a basic concave parabola, at point x equals 5. Let's say I want to calculate the instantaneous rate of change at x equals 5 of the function y equals x squared. Well, then I can just use this formula, right? This is the formula to calculate the instantaneous rate of change at a certain point of a function, right? So since a is a constant, since a is the point that we are looking for here, if I want to calculate the rate of change, instantaneous rate of change of this function at x equals 5, then I just need to substitute 5 in this value to have the instantaneous rate of change of f prime 5, right? So let's do it right now. Let's use the top equation as limit approaches 5, then x minus 5, then then in the place of fx, I'll write x squared, because this is the value of fx, and f8 minus f5. If I plug in f equals 5 here, then it will be 5 squared, which is 25. However, as the x approaches 5, then both the denominator and the numerator approaches 0, right? However, I can factor this out. I can factor it out. So again, limit x approaches 5 and x minus 5. However, this can be factorized into x plus 5 and x minus 5. X plus 5 and x minus 5. And since I already have x minus 5 on both denominator and the numerator, I'll be able to cancel them out, just leaving limit as limit x approaches 5, then x plus 5. Since this limit exists, I can just plug in this number here, which gives me 10 from 5 plus 5. So, congratulations, you have, for the first time in your life, you have calculated the instantaneous rate of change at x equals 5 of the function y equals x squared, which is 10. So congratulations. With the same concept, you will be able to use this formula of the first principles to calculate any gradient of instantaneous rate of change of a function at a specific point by using these two formulas. However, although I use the first formula here, I still recommend you to use this formula if you are running out of time, because as I have said from the before part of the class, this formula is the more widely used and the more widely accepted term of the first principles of defining the instantaneous rate of change of a function at a specific point. Okay, so while we learned all these lots of amount of topics today, I really think review is necessary to genuinely understand these topics, and I can guarantee you just successfully comprehending all these topics genuinely will lead you to a huge success for you in the unit of calculus. And starting from our next lesson, although I do not really think it is that much necessary, you can choose not to listen to it if you want, but I highly recommend you to do so. We will be looking at more of the limit concepts of the first principle that we defined today. So limits have different conditions where it exists or not, right? So we will be using those concepts of the first principles here to define, to look at the specific conditions in which these limits are satisfied or not, or in which the limits can have a different definition or identity or not. So although it is not necessary, I think it is one of the most crucial parts to help you to get a better concept and to get a better hold of conceptual identities of the differentiation. Also, that will be leading you to a success in the integration process as well. So thank you so much for listening today. I really recommend you to review the concepts that we have learned, and we will be discussing about the more concepts of the first principles more deeply next time. Thank you.